Today I'm going to tell you about an important step in the development of telecommunication. In this day and age we take it for granted that we can talk directly to everyone on this planet and that we can even see each other. But that was quite different 200 years ago. You could wave a flag or send a smoke signal, but the reach was only a few miles at best. This only started changing 2 centuries ago. At that time people were experimenting with electrical signals along a copper wire. They learned that you could move the needle of a compass by bringing it close to a wire that carried an electric current. I will show that here. They built a so-called galvanometer that moved a needle showing the direction of the electric current. Here you see such an old galvanometer. When I connect it to a battery, you can see that the needle or the pointer turns to the right. When I swap the plus and minus connection of the battery, the needle moves in the other direction. This movement can be shown at a very large distance by just using long copper wires. The person in the right picture is William Cooke. On the left is Sir Charles Wheatstone. Wheatstone was professor at King's College in London. He is best known for the development of the Wheatstone Bridge, a piece of equipment that he actually not invented himself. These two guys used the principle of the galvanometer to build a telegraph system. Their patent of 1837 describes how it works. I show you here a copy of the drawings of that patent. Their original equipment and replicas are very rare. Here is a photograph of an early version of the apparatus. In those days they wanted the equipment to look nice. Therefore they used oak or mahogany, decorated with elaborate wood carvings, as you can see here. The main components are the diamond-shaped panel at the top and the brass keys at the bottom. I have built a telegraph instrument following the same concept but using modern components. Instead of galvanometer coils, my system has small servo motors. These servo motors are controlled by an Arduino microprocessor. I will tell you later how that works. Let me first demonstrate what it can do. On this diamond-shaped panel you notice the letters of the alphabet. They are printed along lines. And these lines run towards 5 small black pointers or arrows. The arrows can swing to the left or to the right, as I show you now. To the left and to the right. Okay, you say, I get that, but then what is the purpose? The smart idea of Cooke and Wheatstone was to use 2 arrows and a grid of lines on the board to point to a letter. I will demonstrate how you can point to a letter by using 2 arrows. For example, let's say I select the letter B. The letter B is on the line that runs upwards from the leftmost pointer. It is also on the line that runs upwards from the pointer number 4. I turn the first arrow clockwise and have it pointing towards the letter B. I then turn the 4th arrow counterclockwise to also point to the same letter. So by turning the arrows either left or right, I can point at any letter on the board. The selected letter is at the crossing of the lines that run from the pointing arrows. Let me select another letter, for example the letter S. To point to that letter, I let the top of the 2nd arrow turn to the left and the 4th arrow to the right. Both arrows now point downwards to the letter S. The board that you see is the display that the sender sees. The receiver has exactly the same display. The sender and receiver displays are connected by 5 wires, each operating one of the arrows. So the movement of the arrows at the sender are copied exactly at the receiver end. In the same way, the receiver can use his or her apparatus to return a message. You will notice that a few letters of the alphabet are missing. There's no C, J, Q, U, X and Z. These letters can be replaced by other letters without losing the meaning of a word. For example, an X can be presented as KS. Representing all letters of the alphabet would require an additional pointer and its associated sixth wire. This would have made this telegraph system even more expensive. The advantage of the Cooke and Wheatstone telegraph was that it did not require trained operators, but it needed 5 wires and that made it expensive to install. Later telegraph instruments worked with fewer wires. They were cheaper to install, but they required trained operators to work with the coded signals. For those of you that are interested in the workings of my telegraph instrument, I will now go a bit further into detail. In the original apparatus, Cooke and Wheatstone used buttons to turn the pointers. These buttons connected the galvanometer coils to either the positive or the negative terminal of a battery. I showed you earlier how that works. I use switches that have the same effect. This black box has 5 switches that turn the pointers. The switches have 3 positions: neutral, to the left and to the right. The 5 switches are connected to 5 analog inputs of the Arduino microprocessor. Inside the black box you find the Arduino board on the left. At the back of the instrument is a battery box. This is similar to the original equipment that used batteries as well. In my case I use 4 1.5 volt batteries in series to power the Arduino board and the servo motors. I use the analog inputs of the Arduino instead of the digital inputs because this gives me the opportunity to read the 3 positions of one switch from a single input port. The analog input reads 5 volt when a switch is pushed to the right. Pushing it to the left connects the analog input to a voltage divider to read 2.5 volts. In the neutral position the reading is 0 volt. The Arduino microprocessor controls the angle of a pointer by stepping a small servo motor. The position angles are 30 degrees to the left, neutral and 30 degrees to the right. The microprocessor translates the analog input reading into the position angle of the corresponding arrow or pointer. So if a switch is pushed to the left, the analog input reads 2.5 volt. This translates into an angle of 30 degrees to the left. Similarly, if a switch is pushed to the right, the analog input reads 5 volt. That translates into an angle of 30 degrees to the right. The arrow stays in the neutral position if the input is 0 volt. The control lines of the servo motors are connected to digital PWM pins of the Arduino. PWM stands for pulse width modulation. To demonstrate the operation, I will pick a character and turn the arrows in such a way that they point towards that character. Looking at the board, we can see that for the letter B we need to operate the first and the fourth switch. The first arrow has to point to the right, so I push the first switch to the right. The fourth arrow must point to the left, therefore I push the fourth switch to the left. I can do the same for the letter S, where I push the second switch to the left and the fourth switch to the right. This instrument is not a replica of the Cooke and Wheatstone Telegraph, but it nicely demonstrates its operation. This short story summarizes how people started to communicate in the first half of the 19th century. It was only large institutions such as the railways that could afford such an expensive system in the early days. The Cooke and Wheatstone telegraph was cumbersome and expensive to install because it needed 5 wires between stations. Reliable insulated cables did not yet exist, so the wires had to be put on overhead poles. It took a while before the telegraph became popular. One incident generated a great deal of publicity and led to an increased acceptance. There was a guy called John Tawell. He had poisoned his mistress in a place called Slough. She screamed and people saw Tawell running away. He boarded the train to London and the police was notified. They used the newly installed telegraph to send a message to Paddington Station in London, and there the criminal was arrested on arrival. This is the first known application of telecommunication to assist the police. The telegraph became a lot cheaper by using a single wire and the earth as a return path for the electric current. That required the letters to be coded, and telegraph operators had to be trained. The best known code is Morse, after Samuel Morse, who introduced it in 1837 in America. Morse code is still in use more than 150 years later. Letters and numbers are represented by a combination of dots and dashes. A well-known code is the distress message SOS, which is 3 dots, 3 dashes and 3 dots again. I will tell you more about the Morse telegraph in another video.